This lesson is on linear programming applications. Here's our question. Certain laboratory animals must have at least 30 grams of protein and at least 20 grams of fat per feeding period. These nutrients come from food A, which costs 18 cents per unit and supplies 2 grams of protein and 4 grams of fat, and food B, with 6 grams of protein and 2 grams of fat, containing 12 cents per unit. Food B is bought under a long-term contract requiring at least 2 units of B be used for every serving. How much of each food must be bought to produce the minimum cost per serving? So our goal is to minimize cost. Let's keep that in mind. We have to break things down into food A and food B. What does it cost? How many grams of protein per unit? How many grams of fat per unit? So I've tried to highlight the relevant information here. Food A costs 18 cents per unit. Food A has 2 grams of protein per unit and 4 grams of fat per unit. Food B costs 12 cents per unit, has 6 grams of protein and 2 grams of fat. So we've broken it up this way. We recognize, of course, that we have to have at least 2 units of B. So we need some variables here. So I'm going to let X represent the number of units of food A. How many units of food A am I going to purchase? Y is going to be the number of units of food B. So the cost, 18 cents for each unit of A plus 12 cents for each unit of B. So our cost will be 18x plus 12y. Protein. For every unit of A, I have 2 grams of protein. For every unit of B, I have 6 grams of protein. So 2 grams times every unit of A, 2x, plus 6 grams times every unit of B, plus 6y equals how much protein I have. Similarly for fat, we have 4 grams of fat for each unit of A, 2 grams of fat for each unit of B. So 4x plus 2y will be describing how many grams of fat we have. Now, protein, what does it say? Certain laboratory animals must have at least 30 grams of protein. So protein has to be greater than or equal to 30. So 2x plus 6y has got to be greater than or equal to 30. And how much fat do we need? At least 20 grams of fat, so 4x plus 2y has to be greater than or equal to 20. So again, we're minimizing the cost, 18x plus 12y, subject to protein, 2x plus 6y greater or equal 30, and fat, 4x plus 2y greater or equal 20. But also, what does this say? At least 2 units of B per serving must be used. Units of B is the letter Y, so Y has to be greater than or equal to 2. And of course, we can't purchase negative amounts of A, so X has to be greater than or equal to 0. But I want to keep in mind that X and Y have to be positive, so in essence, I want to just focus on first quadrant results. It doesn't make sense for X and Y to be negative, so I'm going to graph these lines only in the first quadrant. So we have 3 of them. 2x plus 6y equals 30 will be one line. 4x plus 2y equals 20 will be a second line. Y equals 2 will be a third line. From there, we want to find our feasible region with our corner points. Test to see if we can find a minimum. So again, there's the function we're minimizing, subject to these, in essence, 4 constraint equations. So let's start with 2x plus 6y greater or equal 30. I will solve this as an equal first. 2x plus 6y equals 30. And I like to solve this using the intercepts. So if I let x be 0, 2 times 0 plus 6y is 30. So 0 plus 6y is 30. 6y is 30, y is 5. So if x is 0, y is 5. That is the y-intercept. If I let y be 0, 2x plus 6 times 0 is 30. 2x plus 0 is 30. 2x is 30. X is 15. So 15, 0 is the x-intercept. So we see that 0, 5, y-intercept 15, 0, x-intercept. Now what do I want to do? I want to test which way am I going to shade this thing. So again, there's 0, 5, and there's 15, 0. Do I shade towards the origin, towards 0, 0, or do I shade away from it? So I'm going to test 0, 0, plugging 0, 0 in. 2 times 0 plus 6 times 0 greater equal 30. 0 plus 0 greater equal 30. 0 greater equal 30, no. So I do not shade towards 0, 0. I shade away from 0, 0. And again, I know x and y have to be positive. I really only want first quadrant stuff here. So in the first quadrant, shade away from 0, 0 will give me this region out here. Shading away from 0, 0, we get it looking like that. So that's the first of our constraints. Let's take a look at our next one. I have 4x plus 2y greater equal 20. I'm going to go ahead and graph the equation. 4x plus 2y equals 20, again using the intercepts. So if I let y be 0 to get the x-intercept this time, okay, 4x plus 2 times 0 is 20. 4x is 20, x is 5. So 5, 0 is the x-intercept. If I let x be 0, 4x plus 2y is 4 times 0 plus 2y is 20. 0 plus 2y is 20, 2y is 20, y is 10. So 5, 0, 0, 10 are the two intercepts that I have. And again, I have to decide which way am I shading, towards 0, 0 or away from 0, 0. So I need to test 0, 0. Plugging 0, 0 in, 4 times 0 plus 2 times 0, is that greater than or equal to 20? Well, you can see, of course, it is not. 0 greater or equal to 20 is no. So I'm going to shade away from 0, 0. So what are those points? 5, 0, 0, 10. 5, 0 on the x-axis, 0, 10 up here. Shading away looks like this. Well, the third piece I have to this is y is greater than or equal to 2. So y equals 2 in the first quadrant is here. Y is greater than or equal to 2 are these pieces, this shaded region above that. So I've got 3 lines all shaded away from 0, 0. So I need to determine what the overall graph will look like and then find the corner points. So these are the 3 lines. Okay, this one has 0, 10, and 5, 0. This one has 0, 5, and looks like 15, 0 way out there. But if we're shading everything out, beyond, 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 beyond. So this is not a corner point because I've got to be beyond this line. This is not a corner point. This is not a corner point. This is not a corner point. It's got to be beyond this line. It's got to be beyond this line. So this would be a corner point here because, again, x has got to be greater than or equal to 0. This is a corner point. This is a corner point. Those are the only 3 corner points that will be on that region. So I'll shade it, see what it looks like. Again, all of these are away from 0. So above this line, above this line, above this line puts us in this region. So that's what we have. Now, which corner points do we get? The only one on the y-axis is 0, 10. So 0, 10 is a corner point. There is no corner point on the x-axis. But we have this point and this point. Now, you could solve the equations, but the computer graphs this nicely for me, and we can see that 3, 4 is this one. Notice 3, 4. 2 times 3 is 6. 6 times 4 is 24. That equals 30. 3, 4. 4 times 3 is 12. 2 times 4 is 8 equals 20. So this point is the intersection of those 2 lines. Y equals 2 gives me 9, 2. 9, 2. 2 times 9 is 18. 6 times 2 is 12. 18 and 12 is 30. So this is the intersection of those 2. So I have 3 corner points. This point 0, 10. This point 3, 4. And this point 9, 2. Identify those corner points. There they are. This is an unbounded region. In the case of an unbounded region, you cannot find a maximum for a standard max problem, assuming all the coefficients are positive. But we can't find a minimum, which is what we're looking for here. So we've got to plug all of our corner points into our original to see which one has the minimum value. So we want to minimize C, our cost, which was 18x plus 12y. And we're going to go ahead and plug in those three corner points, 0, 10, 3, 4, 9, 2. So plugging those in, what do we get? What are we going to get? Plugging in 0, 10, we get 120. Plugging in 3, 4, we get 102. That's 18 times 3 plus 12 times 4, 102. Plugging in 9, 2, 18 times 9 plus 12 times 2 is 186. Now, that's 102 cents, so our minimum cost is $1.02. X represents the number of units of food A. Y represents the number of units of food B. So 3 units of A, 4 units of B will give us a minimum cost of $1.02. So what is that going to tell us then? Minimum cost is $1.02 when 3 units of food A and 4 units of food B are purchased. And that will conclude this lesson.